Hi, everyone. Welcome to Memgraph Community Call. My name is Kruno. I work as DevRel. I'm part of the DevRel team at Memgraph. And Ante, who will be presenting today, is my coworker and my friend. So it is my honor to give the word and the floor to Ante. He will talk about ACID and isolation levels in databases. So Ante, go ahead. The floor is all yours.
Hi everyone, as Kruno said, I'm Ante, and today I will talk about ACID transactions and isolation levels. So let me just share my screen. I hope you can see my screen. Great. Yeah, so this is essentially quite popular topic in the database world because it kind of touches a lot of different components. So the idea of this community call and presentation is to raise awareness of the importance of isolation levels and what are ACID transaction will hold that story and how these things are intertwined and how is that all connected to Memgraph in some way. So the most important question everybody needs to ask for himself is what do we use our database for? Is it the source of truth? Is it some type of analytical workload? Is it some type of short, bursty analytics? It all depends on the type of the ways that people use the database. So for the sake of presentation, let's assume that the source of truth is the use case you want for your database, which means that data consistency and data integrity is very important to you. Plus some other things that are kind of related to database being source of truth. And when we say source of truth, we essentially mean like your whole enterprise or business will depend on the data that is in the database, and you will base some decisions on the source that you find in your data. So when we talk about data consistency and data integrity, ACID transactions will kind of often pop. The reason for that is that ACID transactions are essentially a means of securing data consistency and data integrity. They are essentially present in most of the software that's called database today, and they use the notion of transaction. As I said, it is important from data consistency and data integrity perspective. There are solutions that don't kind of satisfy ACID transaction or some of the ACID properties and partially implement some of the properties, but this is dependent on type of software that we are talking about. So essentially, being an ACID compliant database is always a good thing. For example, Memgraph is an ACID compliant database. What essentially ACID compliance means when we talk like in more general terms. So if you ask Wikipedia or ChatGPT these days, you will kind of see definition similar to this. So A stands for atomicity. Like loosely speaking, this means that everything is presented as a transaction. We typically have like multiple transactions that are getting executed. And you want to avoid that some part of the transactions got executed and some part do not. This is the property of atomicity, which says that everything needs to be completed successfully or everything is failed. Just like to put things in perspective, imagine transaction being run and executed, and at some point you kind of pull the plug from PC, and you don't want that part of transaction that got executed kind of stayed in some permanent memory. You want to kind of roll back all the changes. So this is very important. Consistency is another property. Essentially, consistency ensures that all data kind of follows some rules. This can be like unique properties, some triggers, and so that data kind of stays consistent across the database, defined by some predefined rules. Isolation is essentially the thing that we are going to talk today. If you read the description on the presentation, it ensures the concurrent execution of transactions. But why is that important? Because when you are running a transaction concurrent way, there is a lot of things that can kind of mess each other up. So you start writing to some nodes in graph databases and from multiple threads, and things can go like messy quite fast. So essentially, isolation defines how your database will be protected from concurrent workloads. And if you kind of speak as a to define the isolation, you would say that no matter the quantity of concurrent transaction is being executed, the database should remain in the same shape that it was previously. And durability is the last property of the EAST. It essentially says that everything that is stored in the database should kind of have a permanency if some kind of failure happens. This means that once the changes are committed, losing power on your server should not like result in loss of data. So each of these kind of properties are important for having a database as a source of truth. But we are going to talk today about isolation in a bit more details. So as I kind of previously mentioned, it is important in multi-user concurrent scenarios. As we all know today, it is a very common scenario where you have servers with multiple CPU cores, and ideally you would like to run your database on all the cores available. Although this is kind of not feasible, this will be like ideal scenario. And during that running on multiple cores, a lot of messy things can happen, as I said. So protecting the integrity and consistency in multi-threaded application is important, especially in databases. So if you can see this visualization, you essentially have the database and there are reads coming in and writes coming in and things happening. And you're not sure in what moment something will get executed, and it can mess each other up. There is a popular paper that introduced the ANSI SQL isolation levels. And after that, there was also a follow-up paper that defined a critique of ANSI SQL isolation levels. It was kind of the critique on the standard isolation levels. And the good thing about this paper is that it goes in a lot of interesting details about isolation levels. Although this is a bit outdated paper, it's like from a paper from 90s or 2000, early 2000. But generally speaking, it is a solid ground for understanding what is happening with isolation levels and why are they there. So one of the isolation levels mentioned in that paper are read committed, read uncommitted, repeatable reads, and serializable. And there are also some anomalies mentioned: dirty write, dirty read, fuzzy read, and phantom. But there is also a bunch of other anomalies and a bunch of other isolation levels out there in the world. These are just like some of them mentioned in the paper, but they are like enough to put your head around the basic isolation levels in the databases. So most of the databases essentially implement the databases mentioned in the paper. For example, the first line here is from the docs of MySQL. So InnoDB, which is a storage engine for MySQL, offers all four transaction isolation described in SQL 1992 standard, which is read uncommitted, read committed, repeatable, read, and serializable. And the default isolation level for InnoDB is repeatable read, which is kind of higher isolation level. This is essentially good, but we are going to talk why this is good. And the table below is essentially from Postgres, from their docs. So you have the also mentioned isolation levels: read uncommitted, read committed, repeatable read, and serializable. And there is this kind of anomalies that can happen during the normal process of the database. As I said, this is just like some parts of possible isolation levels, and there are some parts of possible anomalies. There is a bunch more, but just for the sake of the example and presentation, we are going to focus on this segment. Memgraph also supports different isolation levels, but I'm going to talk about that a bit later. So let's then go to one example of anomaly that can happen in the typical multi-user scenario or concurrent workload. So that's the dirty write. And the kind of the storyline goes like this. So transaction T1 modifies a data item, for example, a node. Another transaction T2 then further modifies that data item, that same node. And before T1 performs a commit or a rollback, if T2 or T2 then performs a rollback, it is unclear what the correct data value should be. So why this happens? Because T1 modifies the data item and then T2 again modifies the data item, and you lose the data from when T1 modified something. And if you want to perform a rollback, you're not sure to what you're going to roll back or to what you're going to return. So that's like dirty write. And when you read the papers or when you describe this type of operations, you use special notation for that. So for example, write 1x essentially means this is transaction 1 writing to node X or to data X or to row X, depending on the type of the database you are explaining. So that means write 2x is essentially write transaction 2 that's writing to some node of the data X. C1 is commit transaction 1. A1 is abort or rollback transaction 1. Anything of that. So if you want to explain the dirty write, it will go like, okay, so the transaction write to node X, right? Transaction 2 write to the node X, and if transaction 1 commits or rollbacks and transaction 2 commits or rollbacks, we have an essentially anomaly or an issue because we are not we lost the data integrity here. So this is just like one example. There is also an sample of dirty read, which is a different type of anomaly. Here the T1 modifies data item, and then another transaction T2 reads the data item. That happens before T1 perform a commit or rollback, and if T1 decides to perform that rollback, T2 essentially holds the data that was never committed, so never really existed. If you want to describe this in the method that I just described, so you write something to the node, the other transaction reads that data, and if both transactions are here, if any of these transactions kind of decided to commit or roll back, you have an issue. So what is the implication of read uncommitted? The implication is that you have a boom. Again, if we are running read uncommitted isolation level, you will stumble upon the issue. Why is this interesting? Because you can essentially set read uncommitted isolation level to most of the databases, Memgraph included. And if you have this type of situation, you kind of can have a messy data inside. So how can you solve dirty read anomaly? Well, by increasing the isolation level again to something better suited. For example, read committed. Hence the name read committed, because you're reading just the committed transaction. But that type of isolation level essentially introduce some locking mechanism. So if you kind of look at this table from the paper, degree 0, which is kind of non type of blocking, is you don't need read logs. You can just use some write logs. And then read uncommitted, you don't need a log for reading the data. But if you are using read uncommitted, this will happen. You have, for example, dirty reads, which is not great. Read committed, of course, introduces the read logs, which kind of prevents these things from happening. But yeah, it is not like the only best isolation level. It is very common and very popular isolation level used in a lot of the databases. So what are the implications of raising the snapshot, raising the isolation level? There are always some type of downsides, and usually this type of increasing the isolation level will lead to correctness and to increase correctness, but to lower performance kind of characteristics. So you will kind of risk your execution time and latency with throughput, scalability, memory usage, etc. So you have always this like a trade-off between performance and correctness. There is also a bit introduced complexity in handling the conflicting transactions and edge cases. So the higher the isolation level, the systems become more complicated, but they tend to perform more correctly and have higher correctness levels. So, for example, the third issue or anomaly that is discussed in the paper and very general anomaly that is very known is non-repeatable or fuzzy read. And T1 transaction reads the data item, then another transaction T2 modifies or deletes the data item. And if T1 then attempts to reread the data item, it receives that modified value or discovers that there is no data there. So essentially, this is no non-repeatable or fuzzy read. It goes like this. So T1 reads, T2 writes, and then if you commit that with transaction 2 committing, then the transaction 1 again reads wrong data again. And if transaction 1 commits, you essentially have the wrong data again. Unfortunately, this is both possible in read uncommitted and read committed isolation level. As mentioned, for example, the default isolation level in Postgres is read committed. So, but the Postgres has some special type of handling this non-repeatable or fuzzy reads, which is not defined by the standard. And it is important to understand what type of issues you can get from each of the isolation level. And then again, if you kind of stumble upon the issues you're facing with data integrity, you can again increase the isolation level if your database that does support that. And here is the table from that paper. And you have these anomalies, dirty writes, dirty read, fuzzy read. We didn't discuss the phantom, but essentially each of these isolation level is somewhat vulnerable by this type of anomalies. Obviously, read uncommitted being the looseliest one, read committed being a bit stronger, repeatable read a bit stronger, and serializable being ideal one. So having a better isolation level, that definitely helps, but as I mentioned, it is always a trade-off. So you need to kind of consider what is the best for your application, and in your case, what type of isolation level is optimal for the use case. So what does a Memgraph do here? Memgraph essentially uses a default isolation level as snapshot isolation. It is the stronger than each that we discussed here, except if serializable. So the snapshot isolation is kind of handling a bunch of different anomalies that can happen. but again, being very quite loose in terms of what you can do with concurrent workloads. As I mentioned previously, Postgres is read committed, and as you've seen today, it's not like a bulletproof, but it has some good protections there. They have like this a bit better read committed than usual. And we also support read uncommitted and read committed on top of snapshot isolation levels. And as I mentioned, our snapshot isolation is implemented as a multi-version concurrency control. Why is this great? Because Memgraph, each transaction is Memgraph is essentially has these deltas, and they kind of they have like the special timestamps, which comes from the snapshot isolation, and you can kind of track what is changing. And this enables you to have a very, very good performance in read heavy workloads, which are kind of very common. And especially if you have like a lot of concurrency with read queries, this will be great. What is kind of the downside of most of the isolation levels, and as you kind of increase the isolation levels, is the performance of the write queries. So the writes kind of get impacted a lot, because you need to lock a bunch of stuff with using the higher isolation levels. Yeah, essentially I forget to mention that integral part of increasing the isolation level is essentially the locking mechanisms. And I guess some of you, it may sound familiar, the error that you can receive from Memgraph that cannot resolve conflicting transaction. You can try this transaction when the conflicting transaction is finished. Essentially, this is a good exception to get or error, because Memgraph is trying to communicate that few transactions are probably trying to write something to the node, and it's not possible because snapshot isolation is protecting this. This means your data integrity will be great, and you will have no issue with data consistency. The downside here is you need to handle that type of error, and you need to kind of decide what you're going to do with that. So it's a bit like push to the developer to handle these type of errors, although this may change a bit in the future. So there is also one more interesting paper that came out during the year on this on the database conference. It is developer responsibility or database responsibility, rethinking concurrency control in databases. Essentially, this paper is discussing how we should handle the concurrency error and concurrency bugs, because those ones are kind of very common and very hard to debug. And it was interesting to see that there is like 92 common issues that they detected, and 42 of those 92 issues are solvable by snapshot isolation level. This doesn't mean like the snapshot isolation level is great and the best in the world. It just means that you need to pick some default, and it could be a solid default as a start, because you have some kind of balance between performance ratio and consistency in your data in the database. So snapshot isolation is kind of interesting isolation level from that perspective. And yeah, this paper discussed a bunch of other stuff, not just like how to approach the issues, but how database should be modeled in regards to those issues. So we started this presentation with the question, what do we use our database for? And kind of the storyline so far has been mostly about having the database as a source of truth that contains good data integrity and good data consistency. But what happens if you want a burst of analytical analysis on mostly statistical data sets, where speed is quite important, and not so the correctness of the data that you have in the database? Then you will use some type of analytical software for that, not a database. or you would use special features in the database. So Memgraph, for example, introduced analytics mode in version 2.7. A lot of details are there, and you can read a bunch of stuff in this blog post linked here, which is dealing with disabling multi-version concurrency control for faster import in analytics mode. Essentially, what happens here is you have a lower memory usage and faster query execution, because snapshot isolation needs these timestamps, and it needs the deltas that follow the transactions with the previous data that has changed. And by importing a bunch of data, you need a lot of deltas. You need to keep track of a lot of history of the data, and this can kind of put the pressure on the memory and speed, which is why the analytics mode was introduced. And yeah, that's the great way if you are not concerned with ACID, because there is no ACID in analytics mode. So there is no any type of guarantees and protection running in ACID mode, including isolation levels. So nothing of that works. There is a mention of D here. This is the durability, which is not there by default, but you can manually trigger like snapshot creation and stuff like that if you don't want to lose your data. And there is also some kind of special quirks. There is essentially is a write lock on the nodes and edges, just to not mess up inserting in the nodes and edges. So there will be some like edge cases in that story that will be kind of fine-tuned over the time. And since this mode is quite new, we have a few bugs reported, but it's getting worked on, and it is very nice that you can use the identical system for running an ACID transaction and have like this complete data consistency and data correctness, and you also have this possibility to run without ACID. So this analytics mode proves to be a bit more flexible. Yeah, and that's pretty much it what I wanted to talk. So I can see Kruno, Soren, and Taylor here. If any of you have any questions, I will gladly to answer them.
Oh, thanks a lot, Ante. So let's see, Soren or Taylor, do you have any questions for Ante?
Yeah, I actually do, because you talked about the isolation levels and that it has a default value, but how can I actually set it in Memgraph? And is it global, or can it be limited to specific points on the database?
Yeah, so Memgraph isolation levels can change, and they can be specified on the transaction level and on global level. So you can essentially run something like globally and run something just as that transaction part. So you have the both options are there.
That's interesting. So if you have both options, does it work both ways? So for example, if the database level on the global scale is really strict about the transactions, then can I make the single transaction more or less strict?
Yes, I think you could. The question here is what is happening on the inside. So for example, if you say, I want to execute this transaction with less security, do we need to wait for all transactions to execute and then this transaction will be executed in this kind of special condition? Or I'm not sure about these details. I should revisit the docs, but I'm certain that you can mix the isolation level during the execution.
That's very interesting. Thank you.
So how does that relate to using analytics mode and transactional mode at the same time?
No, so you cannot use the analytics mode and transactional mode in the same time. So Soren essentially asked about running the transactional mode and then changing isolation levels. And when you decide to run in analytics mode, this is like completely different mode. and every transaction in transactional modes needs to end. And once that all transactions end, then the analytics mode can be turned on. And after that point, you're running in analytics mode. So you cannot mix and match the two modes of running, transactional and analytical.
Yeah. It's all teleological. And how do you test those isolation levels that you have mentioned?
Yes, so basically stress testing a database with a different type of concurrent threads that kind of try to write and you are trying to simulate all these scenarios that we mentioned. For example, these 30 reads, 30 writes, you can kind of simulate that and try test on that specific scenarios, which will kind of be the sole test of is the database correctly handling those type of transactions, and this will be essentially the test of the ACID compliance.
As you know, I'm not a database engineer. I'm not developing Memgraph per se. So can you tell me? So regarding, for example, you've talked about dirty read. That you have a second transaction that is trying to read something that it's not committed yet. So it's like it's intercepting it somewhere or accessing it directly from the memory.
Yeah, so
then handling it.
Yeah, so if you don't have if you have a read uncommitted isolation level, and one transaction is changing the data, and since the data is still not committed, you can read it from another thread. So let's say that we change a node that has like a property name A, and this is still not like committed. It's not in the database, but there is a second thread that wants to know what is the value of node name, and it's A. And the transaction before that is changing the name decides, oh, I will not commit. I pull up. And then you have the other transaction doing something that's dependent on the data that is not in the database, that change the state of some other part of the data. And this is like this dirty read that can happen if you're running, for example, in read uncommitted.
I get it. Thanks. Any other questions?
One last question from me.
Yeah.
So the presentation about the ACID levels was very interesting for me because I myself developed an API, and I, to be honest, haven't thought about this security stuff myself yet. And I have a problem because I have two different databases in the backend, and now I need or want to implement similar things. Can I execute something in Memgraph and wait for an external trigger? So or basically I want to split my query. I want to persist something in Memgraph, but want to keep the transaction open. And at a later point in time, when I know that the other database has completely finished, then I want to finish the Memgraph query. Is something like that possible?
If I understood correctly, so you want to run one part of the transaction, then stop the transaction, and then get back to that transaction once you have some other data.
Exactly, yeah. Or at least the confirmation that the other database has finished its part.
Yeah, so I'm thinking, I'm not so sure. I'm not so sure about that you can just like that manually control and stop the transaction and then get back to that same transaction. Maybe this is possible via the query modules. So for example, you kind of execute a query that has a query module inside, and then the query is waiting for the query module to finish, and query module will finish once it gets its data. And if you write that in Python, C++, or Rust, so, and you kind of from any of these languages querying your other database, then you will be able to kind of introduce the data back to this is some of idea that I kind of pop out in my mind, but we can also discuss it on the Discord. The idea you mentioned to just to rethink a bit more later about that.
Yeah, thank you very much.
And Soren, once you ask, so I just checked. Regarding the setting of isolation levels, you can do it globally, you can do it per session, and you can apply to the next transaction in the current session. So these are the options you have when want to run in different isolation level.
Oh, okay, thank you very much.
Yeah. Corona, you're muted.
Sorry. So if there are no further questions, I would stop the recording now for this part. We will publish this recording on the YouTube, so you can revisit it at a later date if needed.